All right. So let's get started. Okay, so for our final exam, we will also cover the things that you already prepared in your midterm. So just for your head up. Today we'll first begin with some advanced topics for the memory management that are not covered in your midterm. And then after that, we will talk about the device. So first of all, if you still remember, like we talked about how CPU does the page table translation or like page table lookup, right? Because if there is, if you already set up the page table and if CPUs, like there's a CR3 register and CPU will read out the base address from the CR3 register and CPU can go one by one level to do the page table lookup. And inside CPU, there is a hardware component called memory management unit, MMU. And MMU is take care of this kind of page table lookup stuff. So today we are going to talk about how like CPU activate MMU, because actually MMU is a hardware component. So when you just boot up your computer, MMU is not activated. What I mean is you need some function to activate MMU before you can start the virtual. So after you set the CP15 to 1, then all of your memory assets should be translated by MMU. So here is an example. Like this is, assuming this is the physical address space. So there is an instruction code to store CP15 to 1, which means you are going to enable MMU. And this step is usually run when the system boots up and it is going to start, it is going to prepare your kernel. So you can think about this is one step of preparing all the kernel stuff. So after running this set CP15 to 1, then MMU is enabled. So you can think about like this is an abstract of CPU. So this is your CPU. So inside the CPU, there are, in addition to the processing units part, there are also cache and there are also a component called MMU. Okay. So if we run this instruction at this moment, like you run like 0x40 at this moment, it means after this instructions, you enable the MMU. Okay. So the thing is, after you enable MMU, all the address should follow the virtual to physical translations, right? So the next, because after you execute 0x40, because for CPU, it will next fetch the next address. So now you will fetch the next address as 0x44, right? So inside 0x44, usually you need a spatial instructions. And this is the goal for this instruction is to jump to like the next function you are going to run. So let's say if your next process or your next function is stored on 0x84, and 0x84 is a physical address, right? So in your instruction for this jump instruction, you cannot write jump to 0x84. The reason is while CPU decode these instructions and then to CPU to go to execute this instruction, CPU will run the MMU to look up this address. So if this address here is 0x84, CPU will think 0x84 is a virtual address. Then after the translation, they will not be translated to the physical address UX84. So actually, this part should be a very special non-address beforehand. So for example, if the system knows the virtual address 0x100 will be translated to 0x84 for the physical address, then your jump instruction here should be replaced to 0x100. So you can have this example like this. So after the CPU enable the 0x40, and CPU will have another instruction called 0x44, right? Because CPU will fetch another one as a neighbor. And in 0x44, CPU will read the instruction from 0x44, and the instruction is called jump instruction. So inside the jump instructions, it is going to jump to a virtual address code 0x100. And because we already enabled MMU, so 0x100 will be translated to like 0x84. So then CPU can jump to this physical address to following on as like process management part. So this is quite important because like before we enable MMU, what CPU will see is it will look like all the address, they are physical address. Okay. But after there is MMU is enabled, CPU will think all of the address, they are virtual address, so that they should be translated to the physical address. Okay, so this is how MMU is so important, because I would say like most of the device now they have MMU. There's only very few embedded or edge device there's no MMU inside. Okay, so this is quite important part. And next thing is about the patch table, because in our lecture we only talk about the multi-level patch tables, right? But because there are also a lot of patch tables stuff, but they're not used by Linux. I mean, there's some other use case. For example, if you are talking about an embedded systems, or you are talking about a real-time system, so they're not used. They don't really need that much of memory capacity, and in that case, maybe you don't need the multi-level patch table. Okay, so there is a quite famous one. Like you can also find this example in your like the dinosaur textbook for the OS. Okay, so this is called the inverted patch table, and the idea is quite simple. So let's first talk about for the multi-level patch tables. I mean, multi-level patch tables, it is quite flexible, because if you have a super large memory capacity, and probably your patch table will be also large, but you don't want to occupy too much of your DRAM to store the patch table, right? Because the more you sacrifice for the patch table, then the less you can use for storing the data. So for the multi-level patch table, the key idea is to partition into several levels. So if the patch table is not used, then maybe you can put inside a storage device like this. Okay. But the thing is, if you are using multiple level patch table, then you will best like for each process, you need one patch table, and also even for inside one process, like the size is growing a lot. Okay. So a very simple idea is, why not just using one patch table? Because if you still remember, when Linux is maintaining the process control block, or like the text structure, data structure, actually there is a thing called PID, right? So if you have this PID and you have the patch number, actually you don't really need the multiple level patch table. I mean, you don't need to maintain a patch table for each process, because you can use the PID to identify which virtual address is belonging to which process. Okay, so the key idea for the single level patch table is like this. The patch table entries will look like the process ID plus patch number and the offset. Okay, so process ID plus patch numbers, you can think about this combination is just like the virtual address. I mean, the virtual address for the multiple level patch table, and the offset part is just like the last 12 bits for the multiple level patch table, just like the offset is going to navigate the location inside one 4 kilobyte patch. So the offset is also in the same functions for the inverted patch table. Okay. So okay, we will talk about this. The process ID and patch number, it is the multi-level. It equals to the function of the multi-level patch table. So you can think about, like, for CPU, what you will get is like the PID and a patch number and a D. The D is the offset, the distance for the location inside each patch. Okay, so actually what we will really use is PID and P, because D will directly use for the physical address part. Okay, so the patch table will look like this. Actually, it will be PID and P, and there's a lot of PID and P. So when the CPU receives one combination between process ID and the patch number, then the CPU will search through the patch table to find out, so where is the location for the corresponding PID and P. Okay, and after finding the location, like you can see here is a thing called I. So this I is the physical address. So you can think about, actually all these PID and P pairs, they will be sorted based on their physical address. So because PID and P, you will get one physical address, right? So you already know that, and you will do the sorting. So after doing the sorting, the location for PID and P will depend where is the if you are getting a very small, a tiny physical address, then PID and P combination will be in a very front location. But if your physical address is super large, then the PID and P will be in the very rear part of the patch table. So it just depends on how large your physical address is, and you will just put the PID and P and then location. Okay. So actually, the patch table, the inverted patch table, is sorted by the physical address, and each patch table entries, there's the process ID and patch number stuff. Okay, so it looks great because you only need one patch table, and the size is not huge because all the process, they only share one patch tables. Okay, but the thing is, if you have several processes and you already touch a lot of patches, somehow your patch table will grow to some size, right? But we say, like, if each time we are going to do the search in this patch table, actually, if there is some PID and P pairs, actually as corresponding physical address is super huge, then they will be close to the bottom to the patch table. In this case, you will need to search through all the patch table. So the overhead is high because you need to check, hey, if the first one, PID and P, match the target PID and P. If not, then you will check for the second one. And if not, you will check for the third one. So the cost will be super high for the table lookup if your physical address is very close to the bottom here. And there is a technical issue, is because we merge all the translation into one patch table. So one physical patch cannot have two shared virtual address. And come to think about, because for the multiple level patch tables, no matter how many processes you have, because they have their own virtual address space, right? So they can share the same physical address. It doesn't really matter, right? Because you have their translation table, and each table, each process has their own table, so they can map to the same physical address. Okay, but if we are doing this inverted patch tables, in the general case, it is not possible to do this kind of stuff, because you can see it is a combination with the process ID and the and a patch. So probably if you have the same physical address, you will occupy the same slot, right? So there is a technical solution for this one, is if you can pay off some extra bits. For example, for this physical address. For this physical address, originally you can only store one virtual address, one PID and P combination. But if you have some extra bits, and then you can maintain a hash. You can think about this just like a chaining list. So you can chain several PID and P here. So you can chain this together, and then you can say, actually, this chaining list, they are all mapped to the same physical address. Okay, so you can use the hashing to solve this problem, but I mean, this will increase the search overhead because if there is a chaining list, sorry, then it means like when the CPU search to this entry, it also needs to look into the chaining list to make sure if the process ID and P is in this chaining list. Okay, so the more chaining lists you use in this page table, then the extra overhead you need to pay off for doing the search. Okay, so this is about several disadvantages for inverted page table. But the thing is, if you are usually, for example, like your mobile phone, okay, just like your Android phone. If you are using Android, actually Android is a variant for like the Linux, right? So usually for Android, each time you only execute one process each time. So for this case, maybe inverted page table can help because there is no multiple processes running in the same time. So maybe with some technical with some technical help, you can use this kind of inverted page table to set some memory capacity. And also, usually inverted page table they will be used in some edge device because usually for edge device you don't have that much of a lot of process. Usually you only have maybe one or two process, and you don't really consume that much of memory. So in that case, if you pick the multiple level page tables, then you need to pay off a lot of memory capacity, but you don't decide for the multiple level page table because if you only have one process, then there is no need for sharing, right? There is no need for sharing the same physical address. So in that case, inverted page table will be a better pick. Okay, so this is just for like different another page table sort of choice. Okay, so last one is huge pad. I mean, huge pad is quite interesting because huge pad is already supported by Linux now, but people doesn't really use that much, and here are several reasons. So let me first give a very brief introduction about what is huge pad about. So huge page is because when we are using a regular page we call it the 4 kilobyte page, just like the page size you already know a lot. And inside the CPU, there is another hardware component called TLB, translation look aside buffer. So TLB you can think about is a very spatial, also like a very spatial SRAM, but with some controller to do some page table entries buffer stuff. So you can see like actually in CPU there are MMU and there is a TLB because MMU will first ask about TLB for if there are already stored entry inside the TLB. If it is, then MMU will directly use the translation result. MMU will not do the page table lookup. Okay. And there is a metric to measure how good this TLB is. What do I mean how good? Actually, how good is how much of possibility this TLB can help to save the page table lookup. Because if the entry is not hit or is missed in TLB, then MMU needs to do the page table lookup. So in current systems, the page table lookup need to go through 4 page tables, right? And each page table means one DRAM access. So you can think about like regular TLB here, actually it is an SRAM. So when CPU accesses the SRAM, usually CPU will only pay for like 1 nanoseconds. So it is super fast. But when CPU needs to do the page table work, then for each page table in the memory, in the DRAM, usually like it will take to like 20 to 50 nanoseconds. So even we say for the optimized case, if like we only take like 20 nanoseconds, but if you have 4 DRAM assets, because you have 4 page tables in our current multiple level structure, So in total, you will pay for like 80 nanoseconds for only doing the translations. So if there is a hit, then you can set like 80 times performance. So for TOB, the measure is how much translation it can set. And it is not hard to do the measure because there is a thing called TOB reach. Actually, I think this is quite general. You can also check it in the computer architecture textbook. So TLB reach, actually the very simple definition will be how many TOB entries times the page size. Oh, this size means how many TOB entries. So the number of TOB entries you can check from your CPU. I mean, if you are going to buy a Intel CPU, and you can first check on Intel's website about what is the spec of the CPU. And usually they will say, hey, actually our TOB can store about like 1100, something like this kind of number of entries. So TOB size is just like mean how many entries a TOB can store. And the key thing is the page size, because in this example, like if we're using the regular page size, then it will be 4 kilobyte, right? But the thing is, because you already know, huge page means the page size is way larger than a regular page. So let's say if your huge page is 2 megabyte, so 2 megabyte is 5 times larger than the 4 kilobyte. So you can, after doing this calculation, the TOB reach for the 2 megabyte huge page systems will be 512. I mean, the matrix will be 5 times larger than the regular TOB. So you can image, if you increase the page size to 2 megabyte, you can save a lot of page table lookup. Okay, so this is a good thing for the huge page. But there is a very strict constraint. There is a very strong constraint for huge page. Is for huge page, both virtual and physical address, they should be contiguous. So what do I mean for contiguous is not only a virtual address, but on your DRAM, you should have a contiguous like 2 megabyte area dedicated for this page. Then it can be a huge page. So if there is not contiguous, then you cannot have this huge page. So this is quite difficult to make this stuff, because I mean, if it is in the very beginning of your system's boot, then it is not hard, because when you're booting, actually there is a lot of free space. So it is very super easy for you to have this kind of huge page. But come to think about, when you run a system for a relatively long time, and you start to like execute, you start to run the process, and you start to terminate the process, then there comes the memory fragmentation in your DRAM, right? The more memory fragmentation there are, then it is harder for huge page to be generated, because there will be a lot of space that there are smaller than 2 megabyte. Then you cannot use a huge page. Okay, so I have a more like stronger example, because the huge page is not only 2 megabyte. You can also change the huge page size to 1 gigabyte. As we already discussed, actually in Intel CPU, you can choose 2 megabyte or 1 gigabyte. And it just depends on the multiple level page table design. So you can choose for 1 gigabyte. So if you choose 1 gigabyte, actually you will be like, I would say like, I think it is about very close to 2 million larger value for the TOB reach compared with the 4 kilobyte. But the thing is, if you are choosing a 1 gigabyte huge page, then you can image, if now you only have the 16 gigabyte of the DRAM, then you can only have 16 pages, right? Because 1 gigabyte, 1 page. So if you have like 16 gigabytes, then you can only have 16 pages in your systems. Okay, so this will be very super strong constraint for current systems. And this is the reason why huge page is not really easy to be activated, because it is quite limited to do this kind of stuff. Okay, and come to talk about some technical stuff, just like if there does really have some cases you can use a huge page, then Actually, for Linux node, there are two ways to offer you to do the huge patch. The first is about directly using a library. So there is a library called the libhugetoBFS. Okay. So this libhugetoBFS is a library can can batch applications, text, data, memory allocation, and share memory with huge patches. Okay, so this one is you directly do the allocations from the user space. Then actually you can directly say what kind of data you're going to store in this kind of huge patch area. Okay, so this one is quite direct because I mean in your runtime you can know if there is enough space to do this kind of huge patch allocations. Okay, and actually there is another way because usually for the programmer, especially for the user space programmer or like application programmers, they do not have enough knowledge to know if this is the right timing to use a huge patch, right? Because when you are writing a C or C++ program, you will not really care about you are going to use a huge patch or not. So actually, this libhugetoBFS is not really popular because most of the programmer will not really care about like you're using a huge patch or you're not using a huge patch. And even the huge patch, they're in different size. So there is a little bit complex for the programmer to do this kind of stuff. So actually, operating system has a design called transparent huge patch. Like the rule is to let the operating system to decide what patches should be a huge patch and could be a regular patch. So there is two ways. One is called a huge patch promotion, which means we are going to make regular patches becomes a huge patch. And there is another thing is called huge patch demotion. So demotion, just like the reverse for promotion, just like to make a huge patch coming back becomes a regular patches. Okay. So actually inside the operating system, there is a inside the memory management, there is a huge patch management here. So what is promotion? So promotion is come to think about if there are two layers. One is the main memory and the other is a swap. Okay. So promotion is if we already say we are going to have a huge patch and in what physical address. So here is the physical address. Then the promotion daemon will move all the required patch from DRAM and then the swap area to this physical address. What I mean, the required patch is all the virtual address because we need the virtual address and physical address to be contiguous, right? So usually what we care about is which virtual address is in this range. Okay, because the physical address usually we will allocate a new physical address to store this data. But virtual address we cannot change it because virtual address is what programmer thinks the data is, right? So what we can do is the OS will check for each related virtual address, and then we will get the physical address. So always can move the data from this physical address to this physical address, but the virtual address keeps the same. So the programmer doesn't really know you are doing a huge patch or not, but operating system can help you to move this kind of physical address, data on the physical address, patch on the physical address to the correct locations. And also the same for the swap area, because like usually if you don't have enough space, you will use swap. So for the transparent huge patch, it is also possible to move those virtual address, they are in the target range, but their physical address, they're not in the target range. So we will just move those kind of regular patches from the swap area to the correct location. Then we will have a contiguous physical address. Okay. So this is about like if the operating system detect actually some virtual address, they are possible to group into one physical address. Okay. Oh, I see a quick question is, what situation will make this promotion? Actually, the promotion will be met by doing some calculation, just like if the operating system check like, actually they are like, I'm not quite sure the key threshold, what is the correct threshold, but for example, actually if there are like more than 2/3 of the patches in this virtual range, they are contiguous in the physical, then we'll do this kind of promotion. But the threshold can be changed. I mean, if this is a 2/3 or this is half or this is 1/3, it just depends on, I mean, there is a system code for you to change about the threshold. Okay. So promotion is like this. So demotion is quite simple. So demotion is just like this huge patch will be, I mean, will be directly demote to a 512 4 kilobyte regular patches like this. Okay, so this, after doing the demotions, then you will get like 512 TOP 512 patch table entries, not one. Okay. So look at this CPU again, because for this design, software is not enough. We still need some hardware support. Actually, in your CPU, there is another like TOB. There is for huge patch. It's called huge TOB, and huge TOB is for the like 2 megabytes. So there should be a hardware for you to enable this like huge patch stuff. So if you have this huge TOB for 2 megabyte, and the entries inside the huge TOB will look like this: virtual address 10 to 522. So it just means there is 512 regular pages, right? Because here the range is 512. So regular page is like 4 kilobytes. So actually 4 kilobytes times 512 will be 2 megabytes, right? So here are 512 and the same. You can map to a contiguous physical address from 80 to 592. This is physical address. And the same thing, the size will be 512. Okay. So this is about the TOB side. I mean, there is also a need for another TOB. So you can think about if you are going to enable a 1 gigabyte, then the CPU needs to have the TOB for 1 gigabyte. Okay. So that is the CPU part it needs to support. So actually, like I would say, like most of the operating system design, I would say maybe not most, but I mean there are a lot of operating system designs they are related to the CPU, because if there is no help from CPU, then those operating system design cannot be enabled. Okay. Okay. So that is the huge patch part. Okay. So once again, the advanced topic were not covered in the exam. So I mean, those like how to enable MMU, inverted patch table, and huge patch, the three things, they will not be in your final. And I think there is a question like, actually, the first sentence is your final exam will also cover all the things you prepare in the midterm. So the final exam will be from lecture 1 to lecture 5. Okay, so that is for the final exam part. So let's move on. Device and block layers. So this is a split view of the kernel. I mean, you can find this very similar figure all the way on the network. So usually, like we have the system call interface to interact with this operating system, right? And below operating systems, there are different hardware resources. Like there are CPU, there are memory, there are disk, there are consoles, there are network. So before the midterm, actually what we learn is the process management part. So you learn about the scheduling, you learn how to create a process, and they are all more related to the CPU. And also you learn about there are virtual address, there are physical address management. So they are for DRAM. And after midterm, main topics, but we will not cover the device control and networking part. Okay. And the reason that we don't really cover, there are two main reasons. One is about because the networking stuff, there is not much of the, I mean, textbook talking about the networking. And another reason is usually the management for networking is very similar to the file. Okay. Actually, like because networking is kind of I/O, so file is also a kind of I/O. So actually, the driver part is very similar to each other. But anyway, we will only talk about the middle part, the file system. from the device to block their driver and file system part. Okay, so before talking about the file system, I think we need to first come back for some arrangement for the things you already learned on the memory hierarchy and storage hierarchy. So first of all, like why we need memory hierarchy? Because you learn this, right? You learn there's a pyramid and the bottom will be the storage, and then there is middle of the memory, and the top is the cache. And the short answer is because it can balance the access time and the cost. Because usually for the SRAM, it is quite expensive. And also the area cost for SRAM is super high. So usually you will have the size of the SRAM is usually a couple of megabytes, right? If you have your CPU and you look at the stack, usually if you have the embedded CPU, then the SRAM will usually be like 32 or like something several hundred kilobytes. And if you have a PC, then usually the SRAM size is like maybe 10 megabyte or like couple of like 10 of megabyte later. So it's quite small compared with the host DRAM. And host DRAM actually, because this is a DRAM structure. So for DRAM, actually the area cost is a little bit lower than SRAM. So you can have a larger DRAM with a cheaper price. So let's say like if you are going to buy a DRAM, like now currently if you pay for like 1 or 2 thousands, then you can have like couple of gigabyte there, right? So gigabyte and megabyte. So DRAM is quite larger than CPU cache, undoubtedly. And also you have the storage, right? So storage device here, there are hard disk drive and SSD, and usually the storage device, the capacity is way larger than DRAM. If DRAM is in the gigabyte level, then storage, we will say that in the terabyte level. Because even currently SSD, it is very easy for you to get a 2 terabyte or like 4 terabyte SSD with a very close prices with DRAM. Okay, so this is about the cost. So there's another thing is about latency. If you once again look at this pyramid, and the right-hand side, I just plot the latency near the component. So cache, or usually like TOB and SRAM, with the SRAM, there is around 1 to 10 nanoseconds for the access latency. So usually for the CPU, if you are talking about a 3 gigahertz CPU, then the clock rate, just like one cycle, is 0.3 nanoseconds. So actually it is very close to TOB and the cache. Okay, and if you move to the DRAM, then the latency will be 10 to 100 nanoseconds. It depends, because DRAM, the structure of DRAM is quite complex. It depends on what is your prior data and what is your next data, if it is in the same very close location or not. So it depends a lot. The latency also varies a lot. And when you look at the storage device, actually the time is way longer. Like it is about microsecond to millisecond level. So it is another like 3 orders slower than memory. Okay, so here is the fast part. CPU cache is super fast, and then the thing is, even currently, because your process usually they are locality, so even you only have a not huge like cache, not large DRAM, actually it is already enough to absorb like 99% of the assets in less in less cache and memory. So which means there are only very few assets will really touch the storage device. And this is also the reason why this balance and cost, the balance works, because if there is no process locality, and if like each of the assets has the same like probability to be assets, then probably like most of the assets will be in the storage. Then this trade-off will not make sense. Okay, so this hierarchy makes sense. There's another reason is because the locality part. Because at the strong locality, so we can do this kind of balance between them. So here comes another thing is operating system. Operating system execution time is between the memory and storage access time. You already know for some like components, there is around like 100 nanoseconds to 10 microseconds. So including like CPU scheduling, context switching, and all those kind of management part. And the reason like actually this time is not so tiny is because you just can, if you check your Linux source code, when you open the scheduling part, you can image about for each functions, and maybe it will be translated into 2 or 3 instructions. So for CPU, it is going to run this instruction, and it is like 0.3 nanoseconds. And usually your scheduler code, maybe it is like several hundred of codes there, right? So this several hundred of codes, if it becomes instructions, usually will be several thousand instructions. So the CPU will take like several couple of nanoseconds to run this Linux source code. So this is the reason why running operating system service, there is still sometimes there. Okay, so because running operating system service needs 100 nanoseconds to 10 microseconds. So for your operating system designs, there are different ways for handling memory or storage access. Because if the CPU is going to get the data from memory, then CPU can directly do the low store instruction. And the reason is it is not a good trade-off to run the operating system, because running operating system is quite slow. So if each CPU and memory access we need to run the operating systems, then you will take more than 30 access in the memory, because memory usually there's only several couple of nanoseconds here. But if you run the operating systems, then you need to pay for another like 100 nanoseconds to 1,000 nanoseconds. So it doesn't really make sense. And this is the reason why we say when CPU access the DRAM, in most cases, we don't really need to run the operating system. CPU will directly just access the DRAM by using the load and store instructions. Okay, but the thing is, how about the storage device? Because the storage device is super slow, so if CPU each time access the storage device directly, then CPU will store there. What I mean store there is usually CPU will stay idle there. So because the kernel designer, the kernel programmer already knows storage device is super slow, then, for example, if we are going to store the data in a storage device, usually like your movie, your photo, your text in storage device, actually we were not directly that created an instructions to do the things like that. So there is a things called like file system stuff. So with this file system, actually CPU can directly use the system code to execute the storage device. Then the system code will trigger operating system will do the file system. Okay, so actually there is 2 very different paths for accessing the data in the memory or in the storage device. Okay. Okay, let's have a deeper dive into what's the difference for accessing memory and storage data. So usually process data and some file data, they are both stored in the memory. So what I mean process data is just like the heap data. You use the memory allocation, or like there is a stack data. So those are called process data. So you can think about most of the things on the virtual address space, they are called process data. And there is another thing is called file data. So file data is like the data usually you are going to store on the storage device, they are called file data. So your multimedia, most of this kind of stuff, they are called file data. And file data, there is also some cases they can be moved to the memory, and we call them cache. Because if we are going to have a better performance, then we don't want always to get the data from the storage device. So we will allocate part of the memory as like a cache to cache those kind of file data. Okay, so for process data, CPU access them by using the load store instructions. But for file data, CPU access them by running the system code and IO stacks. So it looks like this. If there is a process and like in the user space, actually, for accessing the process data, CPU will directly use the load stores. And if there is a case is the data is not in the memory, then the MMU will raise the patch fault. Okay. So patch fault actually means probably the data is maybe in the storage device or in elsewhere in the network device. So we need the help from the operating systems. there is an exception. Because if there is no exceptions, then the CPU can directly use the load store to finish the instructions. And because if here comes an instruction, if here comes an exceptions, then we need the help from kernel. So CPU will trap into the kernel mode to run this patch fault handler. So actually, there are several things for patch fault handler. There is a fault area checking, patch swapping, and context switch. The key rule for fault area checking is the patch fault handler will check what kind of patch fault it is. If this is a major patch fault or if this is a minor patch fault. And if there is a minor patch fault, and what is the reason for this minor patch fault? Is it because there is already a virtual address here, but there is no physical address, or actually there is some permission error because maybe this area is the read-only and now you are using a stored instructions. So here most of the things will be handled by fault area checking to check what is the error. And if the error is the major patch fault, which means the data is not in the memory, then the operating system will then move to the patch swapping part. So CPU will run the patch swapping and then we'll do the context switch. And there is another way, it's called the file data. So file data is because you like programmer, your user programmer, you already know you are going to get the data from what device, right? You are going to the okay, the network is bad. Okay, so for the file data, actually the file system or the operating system gives the privilege to the users to execute, to run the system code. Okay, so when you're inside your instruction, there's a system code, usually means the CPU will ask the operating system to serve for this kind of file IO. So you are going to open a file, read a file, write a file, or whatever you are going to do on those kind of file stuff, it means you are going to interact with the file system. And here is the very simple path for file system. Usually you will check for a patch cache. CPU will check for the patch cache, and if the data is in the patch cache, then CPU will directly return the result to the users. And if it is not, then CPU will go through the file system to get the data from the storage device. And because we are going to get the data from the storage device, so the last step usually will do the context switch. Okay. So this is two different ways for process data and file data. Okay. There is also an interesting stuff as swap. Because if you have an experience to activate swap in your Linux, actually there is a thing called swap file, right? You need to decide how large your swap file is. And the swap file is part of the process data. So swap file is in this, not this. Because for a file that even it is called swap file, but it is not handled by the file IO. Because come to think about, when you are going to access a swap file, in most cases, you will not really read out the swap file and do something. Because for you users, actually, you don't really interact with the swap file. You only say you need a swap file. So when your process doesn't have enough like DRAM resource, then your process will use you push some data into the swap file. So swap file is mainly managed by the Linux like kernel itself, not from the file IO path. Okay, so let's just how the data is accessed in Linux. Okay, so next we are going to talk about the device. Before talking about device, we need to first talk about some very general stuff. What is data? And the very simple answer is a sequence of 0 and 1. So what do I mean by 0 and 1? Here is a very simple example. Given different kind of images, if you are talking about like a white image, then actually in your image, there's only black and white. So black probably you can use 0 to represent it, and white you can use 1 to represent it. Okay. And if you are talking about a grayscale image, because you are going to have a finer color, so you have the black, dark gray, and light gray, and white. So you will have 2 bits for each color. And for this 2 bits image, actually you can only use these 4 different colors to represent this image. And then if you are talking about like a color image, then there are like 256, like there are 8 bits for each color. For example, RGB, so red, green, and blue. So usually you will have 3 8 bytes. So sorry, 3 8 bits. So you have like 24 bits for each pixels. And then you will need like 24 bits. It means you have 2 to the 24 possibility for this kind of color area. So this is about the image. Then there is another thing is called audio, because you usually listen to your like music, podcasts, those kind of stuff, and they're all audio. So audio, because this is a signal, so you cannot directly use like image. You cannot say it is a black or white. So for audio, actually, this is a signal. This is a curve. So people will usually use sampling. So for example, for this curve, maybe you can sample into several points. And sampling, like you can say, hey, actually, how many points you are going to use for sampling, and what's your sampling like mechanism you are using. So probably if you are a 4-bit sampling, then probably you have like 16 bits there. Then you can maintain the 16 bits. Okay. And even using the audio, actually, it is also a sequence of 0 and 1. So no matter what kind of data it is, the basic thing is you are going to interact with 0 and 1. Okay, so I think let's take a 10 and come back later. Okay,就是
我有几个问题，就是关于我影片前面 advance 它那边，
没问题。
就是 MNU 这个部分在启动的时候是 always 去启动，还是主机板上的 run，还是 bootloader？
通常是 bootloader 会去启动，就是可以讲到他说 bootloader 是会帮我们去 prepare kernel，让它可以跑起来。
对，
在 prepare 的过程中，它就会启动 MMU。对。
那它它是放在韧体上，还是说它这个 bootloader 是放在记忆体里面的？
是放在韧体上，
对，
就是或者说应该这样说，它是放在储存装置里面。
哦，它是写在，
就是因为毕竟你开始的时候，你可能会有一个 bootloader，然后你可能会从例如你的主机板上去 activate，一开始要做非常简单的事情。
对啊。
可是你可能 always 这些它是比较多的东西，所以不一定，就是有时候 MMU 是可以在主机上面直接放。有时候如果 你后面有很多要跑的话，它也有可能会放在就是 storage 上面继续去做这样子。
哦，
对对对对对，
那
它是
有说它要放在记忆体上面，它是放在固定的位置，还是说
它是放在它有点像是放在 ROM 的位置。对对对，就是
从开始跑这样。
对，因为它的机体不是 SRAM 或 DRAM，它是主机板上会有一块是你关机它也不会不见的地方。
哦，是。
因为你关机它不见的话，东西就不见了。
对。
所以你东西就一定要从 storage 拿。可是你总要就是有一些方法去 trigger 从 storage 拿这件事情。也就是说，你 CPU 起来的时候，你会需要先做点事情。那些事情只是放在一个不会被删掉的机体上面。那它不是 SRAM，不是 DRAM，通常是很特殊的 ROM 这样的记忆体。对，就是只刻读的记忆体，但是它不会不见。然后那块记忆体的话不会很大，就是可能就是几 KB 这样子。对，然后就看你的规划，就是你要跑多少，因为现在 CPU 越来越复杂，所以它需要驱动的东西很多。对，你可能需要驱动的东西很多，所以你不一定说 MMU 是放在哪里，我觉得还是蛮看你 CPU 配置要觉得放哪里其实是比较合适的。
然后就是看它 CPU 架构是
对
要平衡的。
对。
哦，好东西就是先来一点。
反正那就刚这一段这是什么意思？就是
等一下，等一下，好，你说这个吗？
对啊，
这就是说，因为它这个是因为它是 user library 的部分，所以你在写程式的时候，你可以先说这块两 megabyte 的 user cache 上放什么样的资料。
哦，你是说就可以，
就是你的 virtual address 里面要放什么资料在这个地方。那通常就是说，例如你可能这是2 megabyte，你可能就专门给这个 heap 放这样子，然后这个 heap 这一段 virtual address 就是 huge cache。
哦，你是说直接用 library 去
直接用
分配？
对，没错。 All right, so let's come back. Okay, so because we know like for each data, it's just a sequence of 0 and 1. So it also affects about how to design storage and memory device. Because no matter storage device or memory device, actually the key role is going to store the data. So device consists of material which can switch between two sets stably. They can be either storage or memory or even like CPU cache there are possible. For example, when we talk about a hard disk drive, actually it depends on the magnetic field. If this is a parallel or anti-parallel magnetic field, then it will show, it will represent like 0 or 1. And for SSD, it is about for SSD cell as the voltage value of high voltage value or it is a lower voltage value, then you can decide a 0 and 1. So also for DRAM, like it is using a capacitor. So the charge or not charged, then it represents 0 and or 1. And there are also some very also like very new memory device, novel memory device like ReRAM, PCM, and SCT MRAM. Those kind of, no matter what they are, actually they are depends on the resistance value. If they are representing a high resistance value, then it probably represent 1. And low resistance value, then it represents like 0. So if there is a material, they can switch between like stably between two states, then they can use for this kind of storage and memory device. Okay, and there is also another key thing is because you already know at least for storage device it should be non-volatile. So for the non-volatile things, is it possible to keep the data even when the power of the device is off? So if you power off your computer, then actually all of the data on the DRAM, all of the data in your CPU cache, they will all be cleaned out. So next time you reboot your system, all the data inside the DRAM and SRAM will not store inside. Okay. And the reason after the next time you reboot your system, most of the data like you store in the DRAM and CPU, maybe DRAM is most. In DRAM, it's still there. It's because your computer will store most of the data from memory to the storage device before the power is really off. So the next time you reboot, the data can be fetched from the storage device, and it pretends like the data is in the DRAM. Okay, but actually the capability for storing the data, even there is no power supply as non-volatile device. That is storage device or like hard disk drive, SSD, those kind of device. Even you do not supply any power for this device, the data will not disappear. But DRAM, SRAM, if you don't have given power supply, even there is a power shock, then the data inside those devices will get lost. Okay. So this is about volatile and non-volatile device. So I put several devices like more general device here and then to do some very quick comparison. So first of all, we'll first talk about the cell size. The cell size depends on what is because we say, for example, the SRAM cell, the DRAM cell, and the HDD cell, the NAND flash cell. So you can think about like if we are going to store 1 bit of data, how large the physical area it will spend to store this like 1 bit of data. So for SRAM, actually it is quite huge because you can think about like if you are talking about a storage device like SSD, it is about a NAND flash. So the size for cell size is around 4 to 6 F squared. Okay, so F depends on what kind of nanotechnology you are using, what kind of manufacturing technology you are using. If this is the 2 nanometers, then the F will be like around that 2 nanometer here. So SRAM usually is like 120 to 200. So it is around 2 times larger than DRAM. This is the reason why if you are going to buy the SRAM, the price is quite expensive if you are going to have the same capacity with the same like DRAM. And then for a NAND flash, like it takes about 4 to 6 F squared. So NAND flash or SSD actually is like 10, or no, 15, they're around 15 times cheaper than DRAM. So this is the reason why NAND flash is like even the same price you can have more capacity because the cell size vary a lot between SRAM, DRAM, and NAND flash. Okay. So there are just some supplemental information because SRAM is using 6 flip-flops and DRAM is using the capacitor. So usually they consume way larger cell size. Okay. There is another topic is about endurance. Endurance is if you write a lot of data to the same cell, then the cell will die or like the cell will not function well. And this is called write endurance. So usually for SRAM, DRAM, the write endurance is more than 10 to the 15. So it means for each cell, you can endure more than 10 to the 15 assets. So it also means this device will not really get out of order. But NAND flash actually the write endurance is only 10 to the 4 or 10 to the 5. So for a certain cell, actually you can endure like 10,000 or around 100,000 of the write assets, then you will get you are not working for that cells. Okay, so this is the reason why when you are using the SSD, like if you're using for like a couple of years, then there are some errors comes because there is a write endurance issues for the NAND flash SSD. Okay, and then comes a read latency and write latency. And read and write latency for SRAM and DRAM, they're super fast. Just like the SRAM is around sub nanoseconds stable, and DRAM will be around 10 or more than 10 nanoseconds. But hard disk drive, NAND flash, actually there are more than microseconds, and hard disk drive is millisecond. So it takes way more time to do the rewrite access. Okay, and NAND flash, actually there is a thing a little bit different between the latency is actually read latency is way more faster than write, or you can think about if write latency is quite slow for NAND flash. So there is a synchronous access latency for NAND flash, but the rest of it, like hard disk drive, DRAM, and SRAM, actually they are very in the same scale for read-write latency. Okay, so there is leakage power. So leakage power is if you don't really do the operations on this kind of device, actually for some like SRAM and DRAM, their power will still, I mean, you still need extra power to maintain the data. And the reason is they are volatile device. So you need extra power to maintain the data in the stable state. So for SRAM, actually leakage power is super high. And DRAM, you also need some power to maintain the data there. And for most of the case, like hard disk drive and NAND flash, you only need very few like power to make the data stable. Okay. So there's another energy, it's called dynamic energy, because leakage power is like when the device is in the idle time, then how much energy it consumes. And dynamic energy is when you are going to do one read operations or do one write operations, then how much of energy it consumes. Then here is the table. Like actually, DRAM is in the middle, is in the medium, and NAND flash and hard disk drive actually it doesn't cost too much. Okay, and maturity is more like if those kind of device you can get it on the market. And for SRAM, DRAM, hard disk drive, and NAND flash, they are super mature. And the right hand side, those STT-RAM to FVRAM, actually they are usually still in the lab, so they're still in the test shipping part. Okay. So those are our devices. Then I'm going to do a very quick wrap up about what we are going to learn for the following few weeks. Okay. From the top table, we have the user process. So user process is running in the user space. And user process, if we are going to get the data from a device, and if the data is a file data, then we need to use a system call. Probably you can think about like system call read and system call write to get the data from the store device. And the first component, the first bigger component that we will first pass is the virtual file systems. And then below the virtual file system, there is a patch cache. And then after the patch cache, there is a mapping there. Usually people call them file system. So you can think about this mapping there is more like you are using like ext4 and TFS or max file systems, those kind of stuff. And after the file system, there is block IO layers. Block IO layers, there blocks device driver, and then there is device. Okay, so the yellow part, there are file system, and block IO layer and block device driver, they are block layer device driver, and then there is device. Okay. So for the ordering, we will first talk about the bottom three components, and then we will leave the file system at the last of this course because there are a little bit more things to talk about for file systems. Okay. And for the device part, we will first talk about how data stored in those IO devices. So we will talk about hard disk drive, SMR, and SSD. Oh, so for those you already took the memory storage systems, there will be some overlap here. So, I mean, you can skip it if you already learned it. And then device driver, actually, we'll talk about what are device drivers and how to write a device driver. And if I remember correctly, the third hands-on will be to do some device driver hands-on for the third one. And the block IO layer will talk about like how the system can interact with different hard disk drive or SSD. So block IO layer is going to stay between the file systems and the device. So what like IO scheduler and then what is the block IO, those kind of stuff. All right, let's first move on to the device part. There are two different kind of very famous devices now. One is hard disk drive and the other was SSD. So hard disk drive, if you open up the hard disk drive, actually you can see those kind of, I'll say like hardware layout. And there is an actuator, and here is the actuator arm, and there are the rewrite head. And in the middle, usually there is a spindle, and the spindle will have a lot of platers around the spindles. So the spindle will rotate, and the platers will also get rotated. Okay, so hard disk drive is a mechanical device because most of the components they need mechanical power. What I mean mechanical is actually you need a motor. A motor will trigger the actuator arm to move, back and forth. And then you also need the motor power to drive the spindle to rotate, so the platers can rotate, and the rewrite head can stick to a position to get the data. Okay, so characteristic part, it is cheaper per gigabyte because the plater is not expensive, and it is reliable. What I mean reliable is about the write endurance, because they are using the magnetic to access the data. So actually the rewrite head will not touch the platers. So if you do not like put if the hard disk drive doesn't like have a strong shock or hit on the hard disk drive, actually this hard disk drive can use for a super long time because the data inside it, they can store for a relatively long time. There is no write endurance issues there. On the other hand, for SSD, if you open up SSD, there will be a very different layout compared with the hard disk drive because there is no mechanical component. So inside the SSD, there is only chips. So here is cache, here is a controller chip, here are all NAND flash chips. So the data is stored in the NAND flash chips. Okay. And because there are all solid state circuits, so we call it solid state drives. Okay, because they are using a solid circuit, so SSD is faster than the hard disk drive. And the reason is because for hard disk drive, it needs to wait for the mechanical part to go to locate to a correct direction, the correct locations. So it takes time. But for the solid state drives, actually, it only depends on, I mean, you send the current, you set up the voltage. So those kind of setting is super fast. So this is the reason why SSD is faster than hard disk drive because there is no moving paths. There is no need to do some mechanical control. Okay. And the good things compared to hard disk drive is there is no vibrations or noise. And the reason in the hard disk drive there is noise and vibration because there is a lot of motors inside. So you need to control the filters, you need to control the actuation arm. So there are all like this kind of motor stuff, and they will cause the vibration and noise. But solid state drives, no, there is only circuit control inside. So nothing will do the vibration and noise. And also because there is no mechanical part, so it is lighter and it is smaller. And there is no mechanical head. So in the SSD, usually it supports the random access better than hard disk drive. Okay. More details. Oh. So this is the details of, actually you can think about this is an actuator arm. So for each arm, there are heads at the very front end of each arm. So the head is using the magnet to sense the plater. And on the plater, actually there are two faces, the top face and the bottom face. So you can store the data on the top face or you can store it on the bottom face. It is all available because you have two. Each arm has two heads to sense the data. Okay. And we say actually they are using the magnetic to read all the data. So actually the arm will not really touch the plates. And the reason why some hard disk drive will get out of order is because if you instantly drop the hard disk drive to the floor, or if there is a bump to the hard disk drive, the arm or the head will touch the surface, and it will affect the magnetic on the surface. So if the head is not in the accurate positions, then you will read out the wrong data. Okay, so otherwise, if you give a good protections on the hard disk drive, if there is no auto force to force the hard disk drive to have some like error, actually, their hard disk drive can use for a super long time. Okay, and platers are bound together by a spindle. So here is a spindle. So you can think about there are a lot of platers on the spindles. So this is the reason why hard disk drive can store a lot of data. And for the surface on each plate, actually it is logically divided into concentric circles equal tracks. So each circles, it means one track. So this is track T, and outer will be track T plus 1. Okay, so each track is divided into fixed size sectors. So you can look at it for this track. There are a smaller partition, and we call it a sector. So the size of the sectors will be like 5 kilobytes, and also it is also possible to be the 4 kilobyte. It depends on different hard disk drive. Okay, so let's come to give an example about how to access this kind of plate stuff. So we say here is a spindle, and we just give you an example on one plate, one surface. How to measure how long the disk performance is without optimization, which means if there is no DRAM buffer on this kind of hard drive, then usually there are three main components: seek time, rotational delay, transfer time. So come to think about, here there are three tracks: the inner track, the middle track, the outer track. And on each track, there are couple of sectors. There are 8 sectors. So the outer tracks, there have sectors from sector 0 to sector 7, and middle tracks, they are from sector 8 to sector 15, and the inner track 16 to 23. Okay, so now assuming if we have our rewrite head now points to 22, and if we are going to get sector 2 is here, then first we need to do the seek. So the seek is the time to move the disk arm to the correct track. So because sector 2 is now located on the outer track, and now the head is still in the inner track, so the head should move from the inner track to the outer track, and this is called the seek time. And then because we need to rotate to the plate will keep rotating, and then if we are going to get the data, actually we need to read the head to wait for the plate to rotate to the correct directions, the correct locations. So now if this is 22, and after the rotation, actually, if now this plate now is rotated to like below the head, then the head can read the data. So because the head should wait for a rotation, so it is called a rotational delay. Okay, and rotational delay, actually it can be calculated, because when you are going to buy the HDD, you will see one metric is called RPM. Okay, so RPM is about how many time you can rotate per minute. Okay, so like rotations per minute called RPM. So assuming if the RPM value is like 10,000, so it means like per run, you need to take like 6 milliseconds to finish. Okay, so it is the reason why like hard disk drive is slow, because you can see the seek time is 4.9 milliseconds and the rotation is 6 milliseconds. Even both time can be overlapped together because they can do it at the same time, but it is still a millisecond stable. Okay. Another step is the transfer time. So transfer time is the time to rewrite data to the surface. So because even now it's just about the head is above these sectors, but if we are going to read out the data, so we need to give the head some current to activate the magnetic force. So using the magnetic force, we can read out the data from these locations. So we still need sometimes, but usually the transfer time will not be too long. It depends on how many data you're going to read out. Okay, and this is a simple like summary for how to read out data from hard disk drive. So you can tell actually, as hard disk drive would be on a better performance if the assets there are all sequential, right? Because the rotation is in the same directions. So if you read out the data in the same directions as the rotation, then you can get the data super fast. But if the access is random access, then you need to move the head around the plater. So if the coming request, sometimes you get 18, and next you get 11, and the next one you get 5, then your head should move a lot of seek times, and you need to wait for the rotation delay for a couple of time. So so the random access will seriously affect the performance of the hard disk drive. Okay, so sequential access is just like that, because if now the head is on the outer track, and if the access pattern is 2, 3, 4, 5, 6, 7, 0, then you can just in one rotation, then you can read out all the data. So it will be better compared with if you have a reverse. For example, if you are going to read out like 076542, then you need to wait for a longer time because it's in the reverse order. And a more serious thing is if the access is not on the same track, it is on other tracks, then you need to pay for the seek times. So the more random it is, then the more time the hard disk drive should take to finish the access. Okay, so here comes a deep dive. Then how the rewrite head function, or how to rewrite data, because in this slide we only talk about how to move the correct directions and then to read the data, but how to truly read out the data. So actually like this is the track. You can think about this track. Actually, there are a lot of recording medium on it. So on the track, actually, there are two pairs of recording mediums. Okay, so each recording medium, you can think about it as a magnet. So a magnet, because there is a north pole and there is a south pole, right? So there are also a lot of tiny magnets, and each magnet is a recording medium. And this is a read head, and this is a write head. So read head is smaller and okay. So how to represent the data on hard disk drive? So it is depends on the directions of the magnetic field. So if if we are going to identify it as 0 and 1, it depends on the read head, right? Because if we read the data and then we say it is 0, and if we read another data, maybe it is 1. So it depends on the mechanism for the read head. And then for the read head, if it is about an anti-parallel like magnetic field, then we say it is 0, and if it is parallel, we say it is 1. So okay, so because the hard disk drive using a separated header, so we first look at the read head. The read head is using things called giant magnetoresistance. So this is a physics stuff, but it is not important. What this is important is actually it is telling you you only need a tiny magnet. You can finish this process. I think this is the key takeaway for the giant magneto stuff. And then I do it very simple. This is the very simple illustration for the giant magneto resistance. So this GMR, actually there are two layers. There are free layers and there are fixed layers. So fixed layers means the magneto directions. The magneto directions is always in the same directions. Okay. So the free layer, usually it is using the free magnet. So there is no fixed directions. There's no fixed magnetic directions. And here is the recorded median. So if this GMR moves through this recorded median, then because this recorded median, there are already magnet on it. So when GMR moves through this recorded median, and this free layer will be sensed. So for example, now if there is M pole and S pole on the recording median, then after the GMR moves through it, the free layers will be sensed, and the free layer will get this magnetic field, because here will be sensed to M pole and here is sensed to the S pole when the GMR moves through this recording median, right? So now for this GMR structure, the fixed layer is from the left-hand side to the right-hand side magneto field, and the free layer will be on the reverse, because here is N and here is S. So here is the magnetic field. So the field direction now is from the right-hand side to the left-hand side, and we say the fixed layer and free layer now they are anti-parallel. So because this is anti-parallel, so now the GMR is in a high resistance state because they are anti-parallel. So this structure will become high resistant. And then actually we will given the voltage, the same voltage number, and because if this is a high resistance state, so according to Ohm's law, like voltage value equals to the resistance value times the current value. So we can sense about, oh, actually you have a high resistance state, so your current value will be a tiny current value, right? So we say actually for the GMR, if the fixed layer and free layer is in anti-parallel, then you will get the data as 0. Okay. So here comes another example is if now your recording median is in another directions, let's say this is N pole and this is S pole. So the recording median now is from the right-hand side to the left-hand side. So once again, if there is a GMR move through this recording median, and the free layer will be sensed. So now the free layer will becomes like this, because the N pole will sense to the S pole, and the S pole will sense to the N pole. So the N pole now is on the right-hand side, the S pole now is on the left-hand side. So the magnetic field, the directions is from the left-hand side to the right-hand side. Oh, but the fixed layer is the same. So actually the GMR now inside the fixed layer and the free layer has the same direction of the magnetic field. So they're in a parallel way. And if this is in a parallel, then the GMR will show the low resistance depth. And the resistance value for this GMR will be low because we were given the same voltage value. Sorry, we were given the same voltage value, and according to the Ohm's law, this GMR will return you a larger current value. So we can know, hey, actually now it is in a parallel way. Okay, so if they're in a parallel, then we say actually this recording median is 1. Okay, so this is the way for the hard disk drive to know like where each recording median is 1 or 0. It just depends on the magnetic field inside the fixed layer and free layer, and they will make the GMR to show the high resistance or low resistance. Okay, so this is the read part. Okay, write part is quite simple. Write part is using the inductive write. Okay, so inductive write, actually it is about like this. Inductive write Chinese, I think is called 电流池效应. So given you have a write current inside this circuit, actually you will generate the magnetic force. This is N and this is S, right? And because the magnetic force, I mean, if it is strong or not, it depends on the size of the magnet. So if you have a larger magnet, then you have a stronger magnetic force. So this is the reason why for the right head, it should be way more larger than the read head, right? Because if it is possible, people always want to make things smaller, because if this head is smaller, then you can think about like this. If this head is smaller, then you can pack more plates on the same spindle, right? But the reason now we are using different size of the head, we are going using a separate head, is because we are using the inductive write to write the recorded median, and the magnetic field, I mean the force of the magnetic field depends on the size of the magnet. So the magnet should be on some certain size to support this change. Okay, so actually with this kind of write current, actually here is N and here is S. So the recording median now will change the state. So actually this will be changed to S, and here will be changed to N if you give the current like this. Okay, so this is about how write head works. Okay, so I think here is another problem is, but because this is the magnetic force, so why other neighbor recording mediums are not affected, right? Because actually if you look closer, actually those recording mediums, they are very close to each other, even they are touching each other, right? But actually there is a very small distance. I mean, there is a small distance between each recording medium. And here it shows like there's 8 nanometers here, but actually it depends. I mean, this number, it depends on what kind of hard disk drive you're using, depends on the manufacturing technology. So I just want to let you know, actually there are some very tiny distance between them. So even you give the write current to the right head, the right head will only affect the magnetic field just right below the right head. Okay, so actually they will do the calculation. They will calculate how large the magnet is, so how much the space they need to leave between each recording medium. Okay, because the distance, farther the distance, the magnetic field will become weaker. So it is possible to do some calculation to know what should this distance be. Okay, so this is some brief stuff about how to rewrite the hard disk drive, the hardware part. Okay, but don't worry. Actually, this part, I mean, will not be on your exam. I mean, I will not ask you about please explain about the joint magnetic stuff. Okay, there is no in this final part. Okay, so actually there is a variation for hard disk drive. This is called a single magnetic recording. Okay, so the reason is actually the capacity of the hard disk drive is quite hitting the limitation now. Because now if you are going to buy the hard disk drive, you can get around like 8 to 12 terabyte, right? But it is hard to shrink the, I mean, for example, this recording medium between recording medium, it's hard to shrink to make it more dense because there is a affections. If you make it denser, then the right current, the right head will affect the neighbor. Okay, and also because I mean this spindles, the number of plate on it, it will also limited by the size of the head. Okay, so now hard disk drive is around hitting the capacity limitations now, usually like around 10 terabyte. And there is a way to increase the capacity, and this is called a single magnetic recording, called SMR. And also you can buy this kind of SMR discs on the market now. Okay, so why SMR works? Actually, SMR is only a very slightly technology difference between the hard disk drive. So why it works? Because we say the read-write head is in the size difference for the hard disk drive, right? Read head is quite smaller than the write head. So this, assuming this is our conventional HDD, and this is the track, like for example, track N, and we write the data and we like read the data in this form, right? So what do we find? Actually, you spend quite larger area for a write, right? But you only need a very tiny area for a read. So let's say actually here they are in the same, I mean, they show the same magnetic field, but actually you only need this area to sense out, right? So this is the current, I would say like non-optimization part for the hard disk drive. But you cannot shrink the writer. You cannot make it at the same size as the reader, because if you shrink the size of the writer, it means you are going to shrink the size of the magnet. And if you shrink the size of the magnet, then the magnetic force will not be stronger enough to change the recording medium. So this is the problem. So there is a size difference. It's a truth. And come to think about it, if you can do things like this, if this is a writer and if you move the reader to the left-hand side, and now you do the same things, but a little different is you will overlap part of the new tracks on the prior tracks. Okay, so just like the shingle. So if you go to check the dictionary, shingle is like the wuyan. Okay, so shingle magnetic just mean like we are going to overlap the later track on the prior track. Okay, so it doesn't really affect the reader because actually the reader only read this part. Okay, so with this slight change, we can increase the capacity. You can think about in this size, like you can only store 3 tracks, but given the same size, you can store a little bit way more than 3 tracks, right? So usually if you are using the SMR, it is possible to increase your capacity to like, for example, 16 terabyte, or it is also possible to get the 18 terabyte, just like you will be slightly like another 30% to 50% more capacity than the conventional hard disk drive. But there is also a very obvious challenge here, because we say we are going to overlap with prior tracks. So how about like this? If now, one moment. Okay, no. Okay, so if now we are going to update the data in track N, but track N is already overlapped by track N+1. So now if you rewrite track N again to update the data, actually we will destroy the data on track N+1, right? Because you need to apply another magnetic field to the track N, but now track N and track N+1 they overlap together, so you cannot really update track N. So how to deal with this problem? Actually, people are using the things called the remodify right solutions. So like this, if you are going to update several prior tracks, first of all, we will not really do the right. So we will just mark like, hey, actually this sector, and this sector, they are going to be updated. So we will directly write the new updated sectors at a latest track. So in this case, we will never write to the prior tracks. We only write the new updated data to the latest track, right? So we will write from the current write pointer and we will keep writing. Then we can make sure all the write will be sequential. Okay, so sorry. So those kind of updated sectors, they will become invalid. What I mean invalid is because they are already new data, so we will not really use this kind of embedded sectors here. So those will become like fragmentation stuff. So inside the SMR, actually, there is a problem is how to reclaim, how to run the garbage collection to collect this kind of fragmentations inside the prior tracks. Okay, so this is a new, problem for the SMR device they need to take care of. Okay, so that's it. This is for SMR. Right, so let's move on to the SSD part. Okay, so SSD is using the NAND flash memory. So NAND flash memory is a widely used memory storage technology in today's product. So including USB drives, solid state drives, your iPhone, your Android phones inside their memory, they're using the NAND flash memory. Okay, like all those kind of devices, they are using the NAND flash memory. And there is another thing called NOR flash memory. So NOR flash memory is another technology for replacing the read-only memory, or called ROM. And NOR flash actually it is to store the data like BIOS and firmware, because NOR flash actually it is faster for random read access, but it consumes larger space and actually it doesn't really support the second write. What I mean second write is actually for BIOS and firmware, usually you only write one times and you will not read them, you will not write them, you will not update them. So NOR flash is a better choice because the overhead for doing write on NOR flash is super high. Okay, so this is two different decisions about you're going to use NAND flash or NOR flash. Okay, and this is NAND flash SSD. Like I would say, like all of the SSD now they're using NAND flash. No matter you are using USB or like you are using the enterprise SSD or your iPhone, they are all NAND flash. But maybe you will ask the question as then why there are some USB that are super slow, there are some SSD that are faster, and why your iPhone is way more faster than those kind of devices, even they are using the same technology. Okay, so the reason is even they are using the same NAND flash, but the different NAND flash, like for example, if you given there is a chip, and for NAND flash, in the corner of this kind of chip, they have a better healthiness. Like those chips, those NAND flash chips in the middle one, they have a better health level. So which means you don't really need to do the error correction stuff. You don't really need to worry about there are some error on this NAND flash cells. But for the edge part of this kind of chip, actually those NAND flash memory, they will suffer from a lot of nuance errors. So these arrows actually they need to be correct by the ECC. They need to be correct by extra hardware. So even they are using the same NAND flash memory, but depends on their quality. If you get a higher quality NAND flash, then you don't really need to do a lot of error correction stuff. You don't need extra software optimization on it. So you can get better performance. But if you get a low quality NAND flash, even especially in this kind of USB device, because you're using a low quality NAND flash, you can use cheaper price to buy it. But the payoff is you need to take care of the error stuff. So usually inside this kind of device, you will need extra like ECC to make sure your read-write is correct. So you will take extra time on this kind of stuff. So this is the reason why different device, even they're using the same NAND flash, but the quality is not the same. So the quality will affect, you need to have extra strategy to deal with this kind of error. So NAND flash SSD. So here is the structure for your SSD. We use a 64 GB SSD as an example. And inside the SSD, usually there is a controller, there is a microcontroller. So usually it is going to run some software stuff. And there are also DRAM on the SSD, and it is not few. Usually the DRAM part is quite large. It is around I would say like 1/1000 of the size of the SSD. So usually if you have 64 GB of SSD, then your DRAM should have 64 MB. And the reason is for the SSD, it also needs the mapping table, just like the patch table in your operating system. But there are two very different concepts. I mean, SSD is the management inside SSD, so there is no operating system stuff. But the concept is the same because they are using this kind of patch table like stuff to do the maintenance. So actually it consumes a lot of DRAM. Okay, so controller will be connected to a couple of channels. So in this example, we connect to the 4 channels. So for each channel, you will attach with the chip. So inside the chip, there are dies, okay? And inside the dies, there are planes. So usually there are 2 planes, the left-hand side and right-hand side. So for each plane, there are 1024 blocks on it. And each block, there are 512 patches inside one block. And then there comes the cell. So actually, we say each NAND flash cell is 1 bit or like it's 2 or 3 bits. It is about inside this patch story. So like this, if this is a block, then each horizontal line, we call it a word line. Usually we say here is a patch. Each line is a patch. So on the patch, there are several this kind of stuff. We call it a cell. And a cell means 1 bit, or maybe if you are using a more fine-grained technology, there are 2 bits or 3 bits, but you can think about like this is a bit stable stuff, okay? So this is like the structure of the SSD. And the reason why there are all this kind of hierarchy is for the read-write operations, actually it is in the patch level. So for SSD, or sorry, for a NAND flash SSD, the minimum granularity to read out the data should be a patch. It is really different from DRAM. DRAM, you can say, I'm going to read out only like 1 byte, or like we are going to read out like 64 bytes. It is possible. But SSD, it is impossible. And the reason I will let you know next week, but actually for SSD, each time you need to read out all the cells, all the data on one horizontal word line. Okay. And also if you are going to do the program, if you are going to write the data to this patch, it should also align with the patch level. So if you're going to say to make it like 1111, then you should make all the patches to be programmed. So you need to decide to write in a 4 kilobyte area. Okay. And the thing is, there is a thing called erase. So erase for SSD, just think about just like you're going to delete the data on the SSD. So delete, actually, the size for delete is a block, not a patch. So actually, you need to delete at least 512 patches at the same time. And this is also because of the like hardware circuit architecture for NAND flash. So actually, when you are going to delete a block, you are going to delete 512 pages. Otherwise, you cannot use the delete operations. Okay. Okay, so it's 12 now. So maybe let's call it a day. And let's, yep. Thank you guys.
如果没有空的 chart，它会怎么写？
没有多的 chart 吗？
对啊，就是他现在会把要改的它放在新的 chart，那如果没有多的话，它就没办法到。
他就会把前面的就是做整理这样子，因为前面还是要整理，它只是延后整理而已。
哦，整
理就是它其实有一个 erase 的机制，是可以把这里面的全部清空，所以它就会把这边还有 embedded 的资料全部读出来，读到一个新的地方去，然后把这个全部清空掉，然后这边就清空了。
主要地方是类似那种 buffer 之类的。
没有，就是你可以想到这个 trace 有非常多个，
对，
然后它一次可能会有一个空间是2 MB， 它是可以作为删除的单位，所以每2个 MB 它就可以让你删除一次。对，所以你这边可以讲它有非常多。那我要删除的时候，我就把这边的人复制到这边来，然后这边可以直接删除掉。
那在这里的清空力的是把它设成0还是什么？
清空对，你可以这样想。对，或者就是把它全部归回去某一个就是状态，某个市场状态。
就是没有同一个。
对。哦，好，谢谢。
那为什么这边要
等一下，不好意思，再等我一下。好，来，
因为它为什么这边要排序？
哦，排序就是因为它可以比较好去做这个，因为它这个里面其实放 PID 跟 P， 但是它没有放 physical address。那它为什么没有放 physical address 呢？因为它就是想让它的位置，就是它现在在哪个位置来去决定它是哪一个 physical address。也就是说，它这边想要省去存 physical address 这件事，所以它这边是用排序的方法去做。就如果你可以说你第一个位置是对应到第一个 physical address 的话，第二个位置对应到第二个 physical address 的话，那你就不需要存 physical address，你就看你现在查到这个人是在第几个位置，那他就是第几个 physical address 这样子。
所以它这边会额外储存一个 base address， 然后之后再这样再到。
哦，没有，它这边就是一个 entry， 就是一个 PID 跟 P， 但是呢，你可以知道说你现在是第几个 PID 加 P。第几个就对应到你是第几个 physical 的 page， 就如果你今天假设你这是第10个好了，就是你找到说，你这个 PIDP 在做搜寻的时候，你是第10个，那第10个代表你是拿到第10个 physical page，
第10个 page， 所以它这边就是这个小 page table 是一块连续，然后切割成好几个，
对，你可以这样讲，
对，
每个位置就对应到一个就是位置的 physical page， 这样它就不需要存那个位置了。
然后这个东西又是连续的，
它连续的，
然后它对应的记忆体位置是连续的，
对，对。
然后那最后一个问题是，刚这边提到 OS 选取比较慢，
对，
然后
OS 的执行比较慢，
我也不太懂这边在讲什么，
就是因为 OS 的执行是要时间的，所以基本上 CPU 在存取机体的时候是不会，基本上不会仰赖于那个 OS 的帮助，因为你 CPU 如果要 OS 帮助的话，你就是需要付出100奈秒，可你 CPU 自己去拿 memory 其实就只需要10奈秒而已，那你就自己拿就好，就可以很快。所以这也代表说 CPU 在管理 memory 的时候，通常是采用比较静态的管理，就是它会有一个，比较像是说你的 memory allocation 呢都是静态的，你在管理的时候是跟你存取是两回事，对吧？你分配的时候就是你分配嘛。当你真的要存取它的资料的时候，你是不需要透过作业系统的。你分配完了，那你就开始做执行。那你存取它的时候，就是各种一体的操作就可以结束。那与之对应就是储存装置。为什么储存装置不能让 CPU 直接去拿一拿就结束？是因为它太慢了。所以它拿需要时间。 那拿需要时间的话，你想要避免 CPU 这边干等，所以你就会透过作业系统来去做一个切换这样子。
哦，
对，
好，
对，
谢老师。
问题
好
就是它这个示意图看起来是全画啊，这边它是就是它这个是涨到满，还是说它只有中间这一圈是全
涨到满，
涨到满？
对，它有非常多 trace，
哦，好，所以这就只是一个
它是
示意
地图而已。对对对对对。
然后第二个是就是它为什么这个用 NAND 跟 NOR 它的就是有什么特别？
它的 circuit 架构不一样，就是它的 circuit 去摆出 NAND 跟摆出 NOR 的样式是不一样的。
就是
那不一样的点在于说，NAND 呢它其实可以支援 read write 都可以支援，但是 NOR 的话，它基本上就是读特别快，然后写特别慢，就几乎不能写这样子。
就是它有
对
读
对对对
的效率比较好。
对，
OK，然后就是我们那个期中考成绩大概会什么程度？
有人说这样，要看助教他们改多快，
可以决定一下那个去留这样。
还是你问一下助教，助教刚刚在后面，期中考成绩问。
那个确实，刚刚想要就是
没问题没问题
应该有点
可以。好，谢谢。可以，没问题。
然后是不是现在有固定 IP？
还没，我等下查一下，好像有，我确认一下。